We're talking parametric design and computational methods in architecture.
You got it. And it's not just some futuristic fantasy. It's happening right now, reshaping the skylines and the neighborhoods we live in.
And we've been digging through a ton of research, articles, interviews, all sorts of stuff to get to the heart of how these data-driven, algorithmic approaches are changing the game.
It's a big shift, for sure. I mean, it's almost like we're witnessing a new architectural revolution, comparable to some of the biggest leaps in history.
Okay, so let's start with the basics. Parametric design. I gotta admit, the term itself sounds a bit intimidating, a bit jargony.
It can be, yeah. But the core idea is actually pretty straightforward. Imagine this. Instead of drawing a building with fixed lines and shapes, you create a set of rules, almost like a recipe.
Okay, a recipe for a building. I like that.
Exactly. And these rules, they're called parameters, and they define the relationships between the different parts of the design. So if you change one parameter, like, say, the height of a wall, the whole design adapts, almost like magic.
So it's less about saying this wall needs to be exactly 10 feet tall and more about saying the wall height should always be twice the width of this window.
You got it. And that's where the powers computation comes in. These algorithms, they take those rules, those parameters, and generate the actual forms, the shapes, the entire geometry of the building.
So it's not just about drawing fancy shapes, it's about defining a system, a set of relationships that can generate an almost infinite variety of forms based on how those parameters interact.
Exactly. And this unlocks incredible potential for creating buildings that are not only visually striking, but also incredibly responsive and intelligent. You can design buildings that adapt to the environment, to the way people use them, to all sorts of factors.
That's what I find fascinating about all this. It's not just about aesthetics. It's about creating buildings that perform better, that work better for people and for the planet.
Absolutely. It's about moving beyond the idea of a building as a static object and starting to think of it as a dynamic system, constantly adapting and responding to its surroundings.
So, is this way of thinking, this idea of designing with rules and parameters, is it completely new or are there historical precedents?
You know, it's fascinating. Even before computers existed, architects were using logic and proportions in ways that foreshadowed parametric design. Think of the ancient Romans like Vitruvius, who based their designs on the proportions of the human body.
Right, so they had a set of rules, a system of proportions that guided their design.
Exactly. And in the 20th century, Le Corbusier, a very influential architect, developed a system called the modular, which was also based on human proportions and mathematical ratios.
So the seeds of this idea were there, but it took the power of computers to really unlock the full potential of parametric design.
Absolutely. The real turning point came with the rise of computers in the 60s and 70s. That's when we started seeing the emergence of computer-aided design, or CAD.
Right, CAD. That was essentially about digitizing the traditional drafting process, making it faster and more precise.
Exactly. But at the same time, some real pioneers were starting to experiment with algorithms, with using computers to generate designs based on rules.
Were there any specific figures who were really pushing the boundaries in those early days?
Oh, definitely. People like Nicholas Negroponte at MIT. He was really fascinated by the intersection of human-computer interaction and how that could revolutionize design.
And what about the software itself? Were there any early breakthroughs in that area?
One of the most influential early programs was Sketchpad, developed by Ivan Sutherland. It was basically the very first graphical computer-aided design program, a real game changer.
So from those early experiments, things really started to take off in the 90s and 2000s, right? That's when we saw the emergence of parametricism and all these wild, futuristic-looking buildings.
Absolutely. That period was a real explosion of creativity, with architects like Zaha Hadid, Frank Gehry, and Greg Lynn pushing the boundaries of what was possible with these new tools.
I remember seeing the first images of Zaha Hadid's designs, like the Haydar Aliyev Center in Baku, and being blown away by those fluid, almost organic forms.
Yeah, those were really iconic buildings, showcasing the incredible geometric complexity that parametric design could achieve.
But that term parametricism, it seems like it generated some controversy too.
It did. Some critics felt it was too focused on form for its own sake, and they worried about a kind of aesthetic monotony, a sameness in all these smooth, curvy buildings.
Right. There was a concern that maybe the technology was driving the design too much rather than serving a deeper purpose.
That's a valid point. But it's important to remember that technology is just a tool. Ultimately, it's up to the architect to use it in a way that's meaningful and that serves the needs of people and the planet.
So let's talk about the tools themselves. What are the main software programs that architects are using in this field today?
There's a whole ecosystem of software out there, each with its strengths and weaknesses. One of the most popular, especially in academia, is Grasshopper for Rhino.
Grasshopper, yeah, I've heard of that. It's a visual programming environment, right? So you don't actually have to write code. You connect these nodes and create these visual algorithms.
Exactly. It's very intuitive, very user-friendly, and it's great for exploring different design options quickly, for testing out different parameters and seeing how they affect the overall form.
And it works seamlessly with Rhino, which is already a powerful 3D modeling software.
Right. And then you have Dynamo for Revit, which is more integrated with building information modeling, or BIM.
So Dynamo is more geared towards the practicalities of construction, the detailed documentation and coordination that goes into a building project.
Exactly. It allows you to automate tasks, to generate complex geometry that's linked to all the building information, and to analyze the performance of the building based on all that data.
And what about some of the even more cutting-edge stuff, like artificial intelligence? I imagine AI is starting to play a big role in this field, too.
Oh, absolutely. We're seeing the emergence of tools like Autodesk Generative Design, which uses AI algorithms to explore a vast range of design possibilities and find the ones that best meet the specified criteria.
So you can tell the AI, okay, I need a building that's this tall, that uses these materials, that meets these energy efficiency standards, and it will generate a bunch of options for you.
Exactly. And it can analyze those options based on all sorts of factors like structural performance, environmental impact, cost, even aesthetics. It's pretty mind-blowing.
That sounds like it could save architects a lot of time and effort, free them up to focus on the more creative aspects of design.
That's the idea. And then, of course, you still have the power of text-based scripting languages like Python, which allow for more customization and control if you're comfortable with coding.
Right. And there's also Houdini, which originally came from the world of visual effects, but is now being used in architecture for creating these incredibly complex, almost otherworldly forms.
Houdini is a beast. It's all about procedural modeling, where you define the steps, the processes, and the software generates the geometry based on those instructions. It's great for anything that involves intricate patterns, organic forms, or complex simulations.
It sounds like architects have a pretty impressive toolbox at their disposal these days.
They do. And beyond the core software, there's a whole ecosystem of plugins that extend the capabilities of those tools even further.
Like what are some examples of those specialized plugins?
Well, you have Ladybug and Honeybee, which are great for analyzing the environmental performance of a building, things like daylighting, solar radiation, and energy consumption.
So you can simulate how the building will interact with its environment, see how much sunlight it will get, how much energy it will use.
Exactly. And then there's Caramba 3D, which focuses on structural simulation. You can test the structural integrity of your design, see how it responds to different loads and stresses.
I imagine that's crucial, especially when you're dealing with these complex, non-traditional forms.
Absolutely. And then you have evolutionary solvers like Wallisai and Galapagos, which use genetic algorithms to optimize designs to find the best possible solutions based on a set of criteria.
It sounds like this whole process is very iterative, very experimental. You're constantly testing and refining your designs based on the feedback you get from these tools.
It is. It's a much more fluid and dynamic process than traditional design methods. And it allows for a much deeper level of integration between different aspects of the design like form, structure, and environmental performance.
So let's talk about some real-world examples. Where are we seeing these methods being applied in actual buildings and urban environments?
One of the most obvious areas is in form finding and geometric complexity. Parametric design has allowed architects to create buildings with these incredible curves, these organic forms that were simply impossible to achieve with traditional methods.
Like the Haidar Aliyev Center we mentioned earlier, that building is a real testament to the power of parametric design.
It is. And the Metropole Parasol in Seville, with its undulating timber structure, is another great example of how these tools can create these amazing, almost sculptural forms.
But it's not just about aesthetics, right? There are practical benefits too.
Oh, definitely. Parametric design is great for optimizing environmental performance. You can design buildings that respond to the sun, that maximize daylight, that minimize energy consumption.
The Al Bahar Towers in Abu Dhabi, with their dynamic facade that adjusts to the sun's movement, that's a great example of that.
It is. And then there's structural optimization. You can use these tools to design structures that are incredibly efficient, that use minimal materials, that are incredibly strong,
Like the ICD-ITK Research Pavilion in Germany, they're doing some really innovative work there, using robotic fabrication and bio-inspired design to create these ultra-lightweight structures.
Exactly, and we're even seeing these methods being applied to urban design, with parametric tools being used to model and analyze complex urban environments to optimize things like density, traffic flow, and green space.
The Barcelona Superblocks project comes to mind. They used parametric simulations to design those pedestrian-friendly zones and create a more livable city.
Right, and then there's custom fabrication. Because these designs are digital, they can be translated directly into instructions for 3D printers, CNC routers, robotic arms, all sorts of advanced manufacturing tools.
So it's not just about designing the building, it's about designing the process of making the building.
Exactly. It's a much more integrated approach, blurring the lines between design and fabrication.
So how is all of this changing the field of architecture itself? What does it mean for the education of future architects?
Architecture schools are having to adapt rapidly. They're incorporating more and more computational design into their curricula, teaching students scripting languages like Python, visual programming environments like Grasshopper, and all the principles of algorithmic thinking.
So it's not just about learning how to draw anymore, it's about learning how to code, how to think like a programmer.
In a way, yes. It's about understanding how to create systems, how to define rules and parameters, how to use algorithms to generate designs.
It sounds like a very different way of thinking about architecture.
It is. It's a shift from designing static objects to designing dynamic systems.
And that shift has some pretty profound philosophical and aesthetic implications, doesn't it?
It does. It changes how we think about buildings, how we experience them, how they interact with their environment.
But it's also important to acknowledge the criticisms that have been leveled at this approach.
Of course, there are concerns about aesthetic monotony, about the overuse of smooth, blob-like forms. There are worries about a lack of cultural grounding, about designs that feel detached from their context. And there are accessibility issues, with these tools often being expensive and requiring specialized knowledge.
But it sounds like the field is evolving, becoming more nuanced, more sensitive to those concerns.
It is. There's a growing emphasis on combining computational power with human-centered design principles, on grounding these algorithms in social and environmental values.
So it's not about letting the technology dictate the design, it's about using the technology to serve a larger purpose.
Exactly. And implementing these methods in practice is not without its challenges. There's the need for technical expertise, the demand for computational resources, the importance of interdisciplinary collaboration.
And there's always the risk of over-engineering, of getting so caught up in the technology that you lose sight of the human needs that the building is supposed to serve.
Right, so it's about finding that balance, that sweet spot where technology enhances human creativity and ingenuity rather than overshadowing it.
So looking ahead, what do you see as the future of computational design and architecture?
I think we're just scratching the surface. AI and machine learning are going to play an even bigger role, helping us to create designs that are more optimized, more responsive, more attuned to the needs of their users.
We're going to see more and more buildings that can adapt in real time, that can learn from their occupants, that can adjust to the changing environment.
Exactly. And immersive technologies like augmented and virtual reality are going to transform how we design and experience buildings. We're going to be able to walk through virtual models, experience different design options firsthand, and get a much more intuitive understanding of the spaces we're creating.
It's an exciting time to be in architecture, that's for sure.
It is. It feels like we're on the cusp of a new era, where buildings are no longer static objects, but dynamic systems, seamlessly integrated with their surroundings and responsive to the needs of their inhabitants.
So, to sum it all up, parametric design and computational methods are more than just a trend. They're a fundamental shift in how we think about and create the built environment.
They offer incredible potential for creating buildings that are not only visually stunning, but also more efficient, more sustainable, and more responsive to the needs of people and the planet.
But it's crucial that we use these powerful tools wisely, ethically, and with a deep understanding of their impact on both human experience and the natural world.
Absolutely. The future of architecture is not just about technology, it's about how we use technology to create a better world for everyone.
And for you, our listener, as you walk through the city, as you enter buildings, take a moment to think about the unseen forces, the algorithms, the data that are shaping the spaces around you. How do these computational processes affect your experience of the built environment? What are the ethical implications of this increasing integration of technology into our lives? These are the questions we need to be asking as we move into this exciting but uncharted territory.